Okay, so now let's see how we can do this, solve this period finding problem very efficiently if we had a quantum circuit for doing it. So remember our problem, we are given a function f. Sorry, okay, so we are changing notation again. We are going from n to m, but that's okay. That's a small change. So remember, we have a function f which maps 0 through m minus 1 to some set s, and f is periodic with period r. So r divides m, and with the property that f of x equal to f of x plus r for every x. And now what we are trying to do is figure out what r is. So here's what our circuit for period finding looks like. And it's based on these properties of the quantum Fourier transform that we've already studied. So what do? We start in the zero state, and we apply the quantum Fourier transform mod m. So remember what the quantum Fourier transform mod m will do to the zero state. Zero state meaning, well, so let's see, the QFT sub m is what, 1 over square root m, and then you have this matrix which is ones along the first row, ones along the first column, omega, etc., omega to the n minus 1, so on. But now, what's the zero state? It's this vector, right? It has amplitude 1 for when our quantum system is in the state 0 and 0 otherwise. And so the result of this is this state, right? So it's the first column which is all ones, meaning we end up out here in a superposition sum over all x with amplitude 1 over square root m, x equal to 0 to m minus 1. Okay, so now when we apply our circuit for computing f to this superposition, of course what we get is sum over all x equal to 0 to m minus 1, where this register is in the state x and this answer register is in the state f of x. Okay. So these two get entangled with each other now. But now if we out here do a measurement and measure what f of x is, we'll get some outcome. And let's say that the outcome is f of k for some value k. So now we can ask, what's the new state of this register here? What's the state of these wires? Well, the answer is it's going to be, remember what the rule of partial measurement is. If you measure these wires and the outcome is something, you sort of cross out all those parts of the superposition that are not consistent with this outcome. So you cross out all those x's such that f of x is not equal to f of k. And then you renormalize to get a unit vector, meaning what we'll end up with is a superposition over all those x's such that f of x equal to f of k. But what are all those x's? Well, they are k, k plus r, k plus 2r, and so on, because this is a periodic function with period r. So at this point, this superposition is going to be equal to k plus k plus r plus k plus 2r plus so on, plus k plus m minus r. How many terms are there? Well, there are m over r of them, so you must normalize by square root r over m. Right? Okay, so this slide's getting a little bit grungy, so let's remember this, let's carry this over, and let's try to clean everything up. So at this point, we are in this situation where we made a measurement there, and this superposition happens to be right. So this is k plus r, k plus 2r, k plus 3r, and so on. Okay, so now what happens when we perform a Fourier transform on this? What happens when we do a quantum Fourier transform sub m of this? Well, remember, what are we planning to do? Well, we are planning to do a quantum Fourier transform and then do a measurement. Okay, so there are two rules that we had about quantum Fourier transforms, followed by, so the first was, if we were to cyclically shift the superposition, then the only thing that'll change in our quantum Fourier transform is the phases. So if we are planning to do a measurement right afterwards anyway, those phases are not going to make any difference to us. So we may as well get rid of this cyclic shift, because it's not going to make any difference to the Fourier sampling that we're going to do. Okay, but now what are we left with? We are left with this periodic superposition, which is what we were looking at before. This is our periodic superposition with period r. So what's the quantum Fourier transform? It's just a superposition L times m over r, right, where L ranges from 0 to r minus 1. We have normalization 1 over square root r. Okay, so what do we end up getting? We end up, when we do a measurement, we see a random multiple of m over r. Okay, so here's the upshot. What we did was we managed to come up with a quantum circuit which is efficient, because our quantum Fourier transform is efficient, our circuit for computing f is efficient, and every time we run the circuit, we make a measurement here, and we see a random multiple of m over r. So we see some s times m over r, where s is a random number, s is a random number between 0 and r minus 1. So now, what are we going to do? How do we figure out m over r from this random multiple of m over r? Well, you just repeat this a few times. So you repeat and you compute the greatest common divisor of all the samples that you get. And the claim is that pretty soon you will, the GCD of these numbers will be equal to m over r, because these s's are random numbers between 0 and r minus 1. If you pick random numbers several times and you take the GCD, you are very likely to get 1, because this is an easy argument, because what's the chance that all these s's are divisible by 2? Well, it's the chance that the first of these s's is even is a half. The chance that the second time it's even is a half, and so on. So if you repeat a few times, the chance that you will get 2 is a factor of the GCD is going to be very, very small. And now you can repeat it with every possible factor, and the chance of having that common factor falls off exponentially in the number of repetitions. And so this shows you that that if you take these samples and you take the GCD, it's very likely that the GCD is going to be m over r. But once you know m over r, of course, you can compute r because you know m. Okay, so that's period finding, and that's our basic primitive that we're going to use next time to factor.